Hey everybody, this is Taavi from Dashbird, and welcome to the live online meetup of the Estonian meetup group. Today we have here Gunnar from Opsio, and he will be talking. We will all be talking about serverless, so yeah, the first one is going to be Gunnar, then it's going to be me, and the last one will be Dennis from AWS. So let's, Gunnar, if you're ready, then can you take over?
So let's see if Taavi, can you share my screen as well? Or add my screen? There we go. All right. So hi, everyone. Tonight, I'm going to talk about building reliable serverless applications. And we have a lot to cover, so let's jump into it straight away. First off, just shortly about me. My name is Gunnar Grosch. As Taavi said, I'm an evangelist at Opsio based in Sweden. I have a long background in tech, development, operations, management, and so on. And I enjoy building technical communities. I'm involved in the AWS Nordic community and also in the serverless meetup communities around the Nordics. I've been named a serverless hero by AWS. Very grateful and honored for that. And I have 3 kids, as you can see in the picture. So let's jump into it. The topic for today is building reliable serverless applications. So first off, let's start from the beginning. Most of you probably already know all about serverless or what serverless is, but for context, let's just look at what serverless is. So this is the AWS definition of serverless. Serverless allows you to build and run applications and services without thinking about servers. And this is not so much about the actual servers as it is about what running servers means. It's about letting someone else do the long time work that is involved with running servers, and it lets you focus on maximum business value. And serverless is not only about functions as a service, like Lambda, but the serverless landscape today consists of a lot of different services. So these are the main points around serverless that we usually talk about, that there is no server management, so no need to provision or maintain in any servers. There's no software for us to install, maintain, or administer. The applications that we build can be scaled automatically from 0 and to the highest peaks, or simply by adjusting the capacity units rather than the number of individual servers. And we pay for consistent throughput or execution duration rather than, once again, the server units. And serverless in itself provides built-in availability and fault tolerance. So you, as a developer or an architect, you don't have to architect for these capabilities on the service level, since the services running the application provide them by default. But key there is that you don't have to architect for that at the service level. You still have to put these pieces and services together. So if you ever talked serverless to someone who's perhaps not used to it, you'll probably heard this line that there are still servers in serverless, and there are, but we just don't manage them. And serverless in itself, we like to say that it is a distributed system by default. And this is the definition of a distributed system. It has multiple components located on different machines that communicate and coordinate actions in order to appear as a single coherent system to the end user. And that might as well be the definition of serverless. So with serverless as well, we also have even smaller compute units. Serverless is stateless. We have uncoordinated bits in the application. So it requires buses, queues, pub-sub messaging, state machines, and so on. And it really relies heavily on other cloud services. So we don't have any servers to manage. And that also means that we have some potential sources of failure that we don't or can't control. And there's less heavy lifting for us when doing serverless. We just have to remember that every time someone setups or configures infrastructure, they usually learn a lot about how it works. And as I said, we have, besides functions as the perhaps most common part of a serverless application, we have lots and lots of different services to choose from. And every one of these has their own potential sources of failure and perhaps unknown failure modes. And for each function and for each service, we have separate configuration and security policies. And this is great for control, but it also gives us the opportunity to introduce failure into our applications. And the architectures that we build in serverless, they are usually more granular. It contains more different pieces, more bits and pieces in the architecture. So we like to say that serverless in itself, it has more inherent chaos in the architectures and in the applications that we build. So let's just look at some of the services that we'll touch on tonight. Not going to do a deep dive on each, but just shortly about them. So first off, we have AWS Lambda. So that's the compute layer of serverless usually. And it's a simple resource model. We select a power rating using memory from 128 megabytes up to 3 gigabytes. And we then get CPU and network allocated proportionately based on that. And so this is the event-driven code execution layer. We create a Lambda function that contains code in a specific language, and it does one specific task that we give that function. And it has, as most serverless services, built-in fault tolerance, scaling, and so on. Another serverless service that's used in most applications is Amazon API Gateway. And that's a fully managed API service. It makes it easy for us to build, create, publish, and maintain secure APIs that can scale. So it's fully managed service. So we just have to more or less configure and set it up in the way that we want our API to act. It has support for both RESTful APIs and WebSocket APIs, and we can use either HTTP APIs or the more traditional REST APIs. Then we have a service called Amazon Event Bridge, and that's once again a fully managed and scalable event bus in this time. So it communicates using events, and we can then easily build event-driven architectures, which is becoming more and more perhaps the norm of building serverless applications. We have the simple notification service, which is pub-sub messaging for serverless or for microservices. And this, once again, fully managed service. It contains a lot of features that we can use then to build more reliable applications. And then we have the simple queue service, SQS. And that's a fully managed queue service, once again, for building microservices and serverless applications. And this allows us to handle or queue events, messages, and so on within our applications in an easy way that can scale along with our serverless applications. So briefly also look at how Lambda works as an execution model, which will help us later on when we'll look at some examples. First off, we have the synchronous model, the synchronous invocation of Lambda. Usually in this way, we have an API using Amazon API Gateway, which then for each call invokes a Lambda function and performs some task based on that call. We then have the asynchronous ones that are based on events. And these can use different services. These examples are using SNS, which means when a message is put into an SNS topic, it then invokes a Lambda function to perform something using that event, usually. Or another example is that we're using an S3 bucket. So for instance, storing an object in an S3 bucket, and when that object is stored or updated or changed in any way, it can then invoke a Lambda function to, for instance, manipulate the image, scale the image, and so on. So that's an asynchronous invocation of Lambda. Then we have the stream-based one, where we're using, for instance, DynamoDB or Kinesis. And that might be when there are updates or new events in a DynamoDB table, it then invokes a Lambda to perform something in regards to that item in the database. Or perhaps using Kinesis, we have a lot of information flowing into our application that then is handled by the Lambdas and then perhaps converts them in some way and stores them in a different service. And the last one is the poll-based one, based on the SQS service. So we have items in SQS queue, which then invokes Lambda by its polling the SQS queue. So those are the 4 different invocation types that we're using with Lambda. So just look at a simple web service, the classical one, where we have the client, an API gateway, AWS Lambda, and in the backend, we have a DynamoDB table. So the client performs a call or a get to an API gateway, which in turn invokes an AWS Lambda function, then perhaps stores or retrieves data from DynamoDB, returns that data to AWS Lambda, which returns it to API Gateway, and then to the client. So that's a really simple architecture, but traditional way of using a web service with serverless services. So those are the fundamentals around serverless, which will hopefully help us a bit when we're moving on to the next section. So now let's talk about the word reliable. Some like to talk about perhaps building resilient systems and so on, but I prefer the word reliable, and I'll try to explain why shortly. So reliability is the probability that a product, system, or service will perform its intended function adequately for a specified period. And the important part here, I think, is its intended function. So it doesn't really say that the system has to behave in without failure, but its intended function, that's usually what the users see. They want to be able to log in. They want to be able to store items and so on. And reliability, it is a lot around patterns and practices, the way that we build applications, the patterns that we use in our architecture. And reliability is not the same as quality. So we can have different quality of applications that we're building, but reliability, that's more of a measurement of that quality, that it holds up over time. And we also like to talk about something called robustness, and that's the ability of a computer system to cope with errors during execution. There's a great example of robustness in for instance, let's talk about a flashlight. Using a flashlight that contains one single light bulb, if that light bulb breaks the flashlight won't work anymore. If we're instead using one that has several LED lights or LED lights, if one of those break, the flashlight is robust enough to still give us light output. So that's how we like to talk about robustness in terms of a system. And then moving on to the word resilient. A resilient system can adjust its functioning prior to, during, or following events, and thereby sustain required operations under both expected and unexpected conditions. So resiliency is a lot about how it can adapt to things that happen, the way that a system can still sustain the required operations, even though there are incidents, even though there are errors and so on within the applications. And there's a great quote from Dr. David Woods. There's a lot of other people who've said more or less the same as well, but he says that resilient isn't something you have, it's something you do. So having a resilient system, well, that's more the things you do to make the application resilient. But building an application, well, that's perhaps more about the reliable part. So that brings us then to the building part, when we want to build our reliable applications. And a lot of this might be based on opinions, my opinions around how to do things. So you might disagree, and that's fine. We have a Q&A section in the end, so just bring your questions then. So let's dive into it. And for me, I think this is quite important, that when we're building an application, we shouldn't ask what happens if a system fails. We should ask what happens when it fails, because a lot of applications, or most applications, they fail, and failure happens all the time. And it might be underlying services and so on, or the way we have written our code that fails. But having that mindset, basing it on what happens when the application fails, well, I think that sets us in the right, it's called mood, to build more reliable applications. So first off, and this is not only for serverless applications. This has been used for quite some time when building distributed systems and building systems that are based on microservices. But we want to decouple our architectures. And decoupling, or having a loosely coupled system, well, that's building a system where each of its components has or makes use of little or no knowledge of the definitions of other separate components. So the separate components within the application should be able to function on their own. So that's a decoupling of an architecture. So let's just look at simple ways of doing that with serverless. So we have an application where we're using client storing something in an S3 bucket, and the client gets an acknowledgement that they have stored their item in S3 bucket. That creates an event to, in this case, an SNS topic. And then when we have that event or that message in the SNS topic, we can then create different parts or different services within the application that then base their next action on that event or that message. For instance, we can use an SQS queue to store the event or the message in. We can use AWS Lambda to perform an action based on the event or the message that we created, and a separate Lambda does something completely different. For instance, sending a message or informing someone that something has happened. And that's an easy way. Using SNS is an easy way to decouple applications by simply using the events that are created when we're updating items, for instance. Another way of doing it is using the service that's called Event Bridge. So this is an example where we have a third party, a SaaS provider, for instance, a ticketing system or something like that, that is connected to EventBridge. There are a lot of third parties that have integration with EventBridge, besides the custom integrations you can create on your own. And in this case, let's say that a new ticket has been created in the ticketing system that sends an event to EventBridge. And then from EventBridge, we can do things with that event. Once again, we have a way of decoupling or loosely coupled parts within our application. And in the same way, for instance, we're storing the event in SQS queue. We can have a Lambda function that does something with the event that it received, or perhaps the Lambda function is then able to call the ticketing system, the third party, and do something with the event that it received. And we can invoke step functions to perform something with state machines around the event. And those are some examples. There are a lot of different services that can be targets for events from EventBridge. And in the next step then, well, perhaps the Lambda function stores something in a downstream service, in this case, DynamoDB. And then we can have a Lambda function pull the SQS queue and perform tasks based on the items that are stored in the SQS queue. And using a queue, well, that's a great way to store our events in a way that means that we are able to process them as needed, perhaps rather than when they are actually created. So that's decoupling. Next part is when I'm building applications, I think it's really important to let AWS handle errors and retries in our applications. Probably all of us are used to handling errors and retries in our code. And that's when that is a habit, well, that's something we fall back to and use over and over again. But letting the cloud provider, in this case AWS, handle that, it has a lot of benefits because they probably know better than us how the applications work. So they have a better sense of how to handle different type of errors. So AWS has built a lot of functionality to handle errors and retries. We're going to look at some of those later on, but make sure to use those. So once again, a basic architecture where we have events in Kinesis that invokes a Lambda function and then stores perhaps those events in an S3 bucket. And if there is an error then, which means that we're unable to store events in S3, perhaps in the way we're used to doing it, well, it is writing our own logic to handle those errors and handle those retries. But instead, we can use the functionality that we have within the services that AWS offers. Different error types, for instance, might be exceptions in Lambda. We can have timeouts, we can have the throttling issues, and so on. And that makes it harder for us to handle errors and retries within our code as well. Because then if we, for instance, run into timeouts, well, that means that the invocation will be aborted. Then we're unable to do anything more with the event or with the error that happened within the Lambda function. So we should try to fail up the stack, let services higher up in the stack handle the errors and the retries. Avoid as much as possible to catch errors using the try-catch method that we're perhaps used to. We should instead let fail the function and let AWS handle it, as I said. And we can, of course, also configure different retry functionality, which I'll show shortly. I like to build my functions with least amount of code possible. So we should have lean functions that have a single purpose. This is optimal, of course, but it's not always possible. But when we're able to, we should have single-purpose functions. So they are as lean as possible, contain as little code as possible. Having removed error handling and retries and so on from it, that's the first step for getting more lean functions, of course. But having single-purpose functions, that gives us the possibility for total failures. So that means failures that we can pass back to the invoking service. For instance, if it was invoked by SQS, for instance, or SNS, well, then we can pass the failure back to that invoking service. All right, so retries. Well, as I said, retries are good, right? And retries, they are a vital part of a distributed system. When we don't have to build the retry logic ourselves, well, that's good. So there are a few things to keep in mind regarding retries. For instance, that the same event can be delivered more than once when we have retry within our application. And for that reason, we often talk about idempotent operations. And that means an operation that can be repeated multiple times and always provide the same result. For instance, setting a user account to active, or check that a record in a database exists and create it if it doesn't exist. So no matter if we do those operations 2 times, it can only set the user to active because it sets it to active twice, or it can only add the record 1 time, because the second time, well, it checks first to see that the record exists. But instead, adding $10 to a bank account, that might perhaps be handled differently, because doing that twice might cause issues in the application. So synchronous lambdas, they return failure to the invoker for retry. Some invoking services retry themselves. I think we have Alexa and Cognito as examples there. Others do not, but they can instead return errors to the client. So think about synchronous Lambda with the API gateway in front. It means that if the Lambda fails, instead of doing a retry, it returns the error to API gateway, which is returned to the client. So we will then have to handle that error on the client side, front end, for instance. Asynchronous lambdas, they will retry up to 2 times and for 6 hours. So we have different settings here: maximum retry attempts and maximum event age in seconds for configuration of retry behavior in asynchronous lambdas. The stream-based lambdas, they store events up to 7 days and up to 10,000 retry attempts for us. So we have configuration there as well for how many attempts we want and how long we should store the record. We can, for the poll-based lambdas, it will return the message back to the queue, to the SQS queue, and it can do that up to 1,000 times for retry. And that is then also configured using max receive count setting. And errors that we have, they fail the entire batch from the queue. And the SDQs, they retry in different ways between different runtimes and different services. So this is important to have a look at based on the SKs that you're using. So there might be different retry counts and different timeouts, and it depends on the service that's used then. But they all have automatic retries and exponential backoff. And we should be aware of what's called a retry storm. Because say that we have a downstream service or a third party that has an issue. Well, if we have lambdas trying to do something with that downstream service and they are failing, well, the retry and so on, that will keep trying. So based on our configuration with retries, it might create a bigger issue for the downstream service. All of a sudden, we'll have lots and lots of Lambda invocations trying to reach that service. And talking about retry storm, well, that brings us to the next topic, which is the circuit breaker pattern. And this is an old pattern in architecture and in application design. And the basic idea around circuit breaker is quite simple. So you wrap a protected function call in a circuit breaker object, which then monitors for failures. So once the failures reach a certain threshold, the circuit breaker trips, and all further or the next calls to the circuit breaker return with an error instead. So without the protected call being made at all. So that's the circuit breaker. And in this case, for instance, we have a Lambda trying to reach a third party. Well, in between there, we have a status check to see that the third party is responding as intended. So if there is a failure, well, after a set number of consecutive timeouts, we trip that circuit. So instead of Lambdas keep trying to reach the third party, it fails fast instead. And then we every now and then keep trying the third party, but not that often. And if it starts working again, well, sure, then we can call the third party once again. And the state of the circuit breaker, it can be either stored in memory, which has a few drawbacks. For instance, if we spin up more Lambdas of the same function. But in this case, we're using a DynamoDB for state of the circuit breaker. We can also use Elasticache or a bunch of other services as well for that. So that's a circuit breaker. We should try to use dead letter queues to capture events that fail to process. And this can be events or messages based on what they are. We can then inspect these failed messages and replay them. So let's look at a way of doing that. We can add DLQs to either SNS, SQS, or Lambda. And SQS, well, it uses SQS as a dead letter queue. So we set up a second queue to use as the dead letter queue for SQS. And they are sent there when the maximum receives value is exceeded. SNS also uses SQS as a dead letter queue. So we can then attach a DLQ to a subscription, an SNS subscription. That's important. It's not a topic, but a subscription. So messages to SQS or Lambda, they are retried, I think it's 100,015 times. When it's SMS, mobile, or SMTP, it's retried 50 times over 6 hours. And for HTTP endpoints using SNS, we can set a custom retry policy. And Lambda, well, it can use SQS, SNS as a dead letter queue. And Lambda will then write the event object that invokes the Lambda function to the endpoint, to the dead letter queue, after the standard retry policy. And it might look like this. So we have an S3 bucket, something is stored there. We then have a Lambda function that is invoked, and that is then storing or creating a message in SNS, which should be delivered to a client. If the message is unable to be delivered to the client, we can store that message in a dead letter queue, in this case, SQS. And that message that we store there, well, we can perhaps replay that event using a different Lambda or the same Lambda to then process the event once again based upon what it is. So that's a dead letter queue. And we have a rather new functionality in Lambda that's called Lambda Destinations. I think it was released at reInvent last time. And Lambda Destination lets us capture function failures. And when it comes to lambdas, we should favor Lambda destinations over dead letter queues. And Lambda destinations can be used for asynchronous Lambda invocations, so invocations from S3, Event Bridge, and so on. And this routes an execution record based on the function result, and the result is either success or failure. And we can then use as a destination for this record, we can then use another Lambda function, an SQSQ, SNS, or Event Bridge. The record that we are sending, well, that contains details about the request and the response in JSON. So an example of that, in this case, we have Kinesis invokes Lambda storing objects in S3. We've seen this before. And then if there is failure, we're unable to store the event in S3, for instance. Well, we can then set up Lambda to have an on-failure delivery of that event into SQS, for instance. And then we can use that event to either look at what happened, or we can use it for replaying and so on. All right. Then we have the subject of fallbacks. Fallbacks, it's something that I think is great, but fallbacks should be used often. And fallback, what it is, it's a contingency option to be taken if the preferred choice is unavailable. Think about a third-party service, for instance, let's say Twilio. We're using that to send messages to clients. All of a sudden, that's unavailable. Well, we can then perhaps use SNS as a fallback instead. And that's a great way of doing it. It could be the same for databases and so on as well. But if it's used often, and there was a message on Twitter just the other day from Mark Brooker. He's one of the awesome AWS engineers that makes AWS Lambda the great service it is. So he posted a link to the builder's library from AWS on a topic, avoiding fallback in distributed systems. And that's something that AWS themselves, they think that we should avoid fallbacks. And the main reason for it is that is the reason of latent bugs. Fallback code usually runs less often, and it's harder to test, which means that perhaps it won't work the way intended when we actually need it. And this started a lot of interesting discussions on Twitter, and it brought out, not least, a few people from Netflix, and they talked about their experience using fallbacks. And Netflix uses fallbacks quite a lot, and they test them using chaos engineering. So they make sure to use their fallbacks often. And that means that fallbacks might be a good option. So then on to what's called verification. And verification is a way of, well, it tells you why it's important to explore a set of conditions in your applications. And we as an industry are usually quite good at reactive measures. Think incident response, disaster recovery, different testing methods, and so on. But verification is more of a proactive experimentation for verifying system behaviors. So verification tells you why it's important to explore a set of conditions and the impact that has on something you care about. So let's just briefly look at that. We do it following a few steps. The first one is we set up the objective, and that's something you care about, something that shows that your system is available and working as intended. Might be page loads, clicks per second, processing speed, and so on. And the objective can be defined at the business level, I want 200 clicks per second, or it might be on a technical level. My purchase API should respond in less than 400 milliseconds. And then we need to set up measures. The objective that we have must, of course, be measurable. So we might, for instance, track the number of clicks per second, and then we add 200 as a threshold, or we measure the purchase API and add the latency as a threshold, the one we defined earlier, 400 milliseconds. And then we add different conditions to this. And conditions reflect an event that could occur in our system. And this is the chaos engineering part of verification. So we're actually using chaos experiments to add different conditions. So we can add an experiment to help verify our application. So what if we add an additional 100 millisecond latency to each API call? Will the API still respond in less than 400 milliseconds? What if there is a downstream service error? Will we still get 200 clicks per second? So with the objective, the measures, and one or several conditions in place, well, we can then verify our system behaviors. So if you're a site reliability engineer, perhaps you can think of objectives as the SLO and the measures as our SLIs. And the condition, of course, is an event that might occur. So looking at our simple web service that we saw early on, we can then set up, we have our objective that it should respond, the API should respond within 200 milliseconds. We have measures in place. We then add the condition by adding latency, for instance, to Lambda in this case. And then we're able to verify that the application behaves as intended. Another example is this. Kinesis streams data, which invokes Lambdas to store data in S3. Well, we can inject errors or exceptions into the Lambda function, which should then, if our application works as intended, it should then have a destination, on failure destination, and store that in SQS, for instance. So that is a bunch of different things to think about when building reliable applications. I'm probably well over my time already. So with that, I'm going to leave it back to Taavi.
Okay, now I'm not muted. Thanks, Gunnar. Really appreciate the talk. So we're a bit over, but I don't think it will be a big deal. So I'm gonna start my talk now. So I'm going to be talking about serverless learnings from real life. So the intent of this talk is to kind of give you, if I was like 4 or 5 years younger in my serverless journey, these are the areas that I would have liked somebody to kind of tell me and kind of lead me into those areas and kind of tell me that, okay, you should be focusing a lot more on those areas than I did at that time when I got started. So a short intro into myself. I've been developing different systems for over 12 years. I've been building serverless applications for the past 5 years. I'm the CEO and co-founder of Dashbird, which is a serverless monitoring platform. Today, we help over 7,000 organizations to be successful at running serverless cloud applications. And you can reach me at Taavi@dashbird.io. So the agenda today is basically high impact areas to focus when building on serverless, and kind of the underused concepts and common challenges that we often see customers facing, and kind of ways to improve and learn as well. If you're going serverless or if your organization is already on serverless, kind of the framework of how to go about learning and improving. So let's start with the high impact areas, and we're going to jump right in. So I think that is the topic that we struggled the most when we were starting, and I still see a lot of our customers and serverless users kind of not spending enough time on the question, and kind of I think this also has one of the biggest impacts down the line. So my theory is that what I've observed from the market and from different developers is actually the time spent on choosing the right services and the best architecture patterns is, I would say, one of the biggest factor of ensuring performance, cost efficiency, reliability, and robustness of the application down the line. And also looking at different applications that are on serverless, issues usually are also caused by poor architecture and service choices. Most well-built serverless application use clever ways to combine different managed services and kind of piece them together like a puzzle. And I think you have to be quite creative, and the kind of hard thing is knowing the different, like all the different services that AWS offers you, and kind of where are you making compromises and what are the strong suits of each one of those services. And for that, kind of the best thing you can do is research a hell out of this. And kind of if you're thinking about building a new part of your infrastructure or your application, I think one of the things that has been our process for the past 2 years, I can safely say, is actually it starts with identifying and researching all the possible tools for a specific functionality. We consider kind of the latency, cost implications, scalability, operation overhead, monitoring, and kind of, what are the possible failure scenarios for those services. And we're always making reasonable compromises between services, or when we choose one service over another. And it's always kind of, the levers are like cost, performance, robustness, and kind of also how quickly we are able to build it using those services. One of the things that helps us a lot is mapping out product requirements. So the initial kind of way we were building stuff was just kind of doing a proof of concept and kind of started building as early as possible. With kind of, as we've evolved and as time has gone by, what we've started to do more is kind of think about, okay, what are the requirements, and what's actually the desired latency that we're looking after, or how many requests we're getting, and then that kind of also make some of the decisions for you. So if you're desiring a latency of sub 5 milliseconds, then that puts some limitations on what services you can use, where you can store your data, those kinds of things. So yeah, that's kind of one element that would help you. Just kind of, common dilemmas here. It's usually databases that you need to be cautious of, or you need to think more deeply. API gateway versus load balancer. Like, I think that dilemma is more around if you want something that's really kind of specific and has a lot of capability versus something that's much more simpler, but it's also a bit quicker and a lot more cheaper as well. And I think the interesting part also is choosing the right compute platform for specific tasks. So it doesn't always need to be Lambda. Things can be serverless and not use Lambda. So you really kind of have to navigate. Like if you're doing like really high scale data processing, you might be using something that's a bit less abstracted. If you're building a GraphQL API, then you might use AppSync. So yeah, think deeply into the compute selection as well. I think the second part that we see the most kind of multiplier and kind of the biggest mistakes being made, the biggest challenges faced is architectural patterns. The reason this is because serverless is so much different from server-centric architectures, and the shift is also that you're kind of pushed towards using managed services, and like kind of the surface area of your application that actually uses compute or like pure functions and like code is reduced. So you're forced into, or not forced into, but you should be using different managed services from AWS. And that really can save your ass down the line. So as Gunnar went deeply into that, I'm not gonna go over it too thoroughly, but decoupling and async patterns is really important. That increases the scalability and robustness of your applications a lot. Avoiding orchestration in code, that opens up a lot of ability and a lot of opportunity to kind of be more reliable, build quicker. And generally don't build what you can reuse from what others have done before. And that also is a contribution to your architecture, because most of those kind of applications are really well thought out of, and kind of you can just use those. So don't spend too much time creating undifferentiated value. Quickly into the async messaging patterns. So one of the things we've seen happen countless times with serverless is basically Lambda can scale really well, but the downstream services might not. And that can result in throttling and exhausting database connections and in a lot of different problems. And that's kind of the first thing that you will probably run into if you don't use async patterns and decoupling. So just an alternative flow here. You could add an SQS and a dead letter queue, and that and reserve the concurrency of your functions, and that will actually protect your downstream services, and your load will be more constant, and you won't have huge spikes. So that's, I would say, one of the most important shifts in the ways of building applications. And yeah, the other is workflow orchestration. Don't orchestrate in code. Don't wait in code as well. If you're waiting in code, you're paying unnecessary money. Implement retry and rollback mechanisms. So that's really important, and it's difficult to do without kind of not using step functions or workflow orchestration. Error handling is built in, and that would be like a semi-serious problem. There are other ways of solving it, but without step functions. But I would recommend considering step functions. And kind of if you're using step functions, it makes it easier to glue single-purpose services into your workflow much more easily, and that you can actually take pieces of code that you can just replace, or you can insert stuff into a database or whatever kind of more easily. Yeah, and I recommend looking into the serverless application repository. Don't build what others have already built. Reuse the things, and that will enable you to get to market quickly. And most applications there are quite well built and reliable, so you can be quite comfortable with using those. So that's the second. The third one is that we see a lot of teams struggling with is generally the developer workflow and the operational tooling. So the problem here is that we see a lot of time being spent and a lot of effort going into basically looking at and navigating data, digging through logs, trying to understand what is going on in your application. the complexity has also shifted from the code level into infrastructure level, which means that kind of the patterns and the way applications are built can be a bit more difficult to comprehend, or at least it's kind of, they work in a different way. And that kind of plays into that you've spent a lot of time trying to understand what's going on. Also, if you're using like a lot of different services, you would need to develop deep know-how into each one of those services. So you need to know how DynamoDB can fail, how step functions can fail, how Lambda functions can fail. So that's kind of a problem that will probably like eat up a lot of time and resources. And like generally you have less control over services as well, and it's harder to attach agents because a large part of your infrastructure is managed services, and it's not code. So that's one of the problems that you're going to develop, and you should be mindful quite early on, because as you kind of scale, it will get harder and harder. So yeah, I would say that if you're thinking about monitoring and debugging, the biggest lever and the most beneficial thing you can do is decrease the time to discovery. So that's the time when something breaks to the time that you actually understand that something has failed. So if you can reduce that time as much as possible, then that's kind of the best scenario starting out, because then you're able to quickly respond to issues. Generally, diagnosing an issue takes less time than just knowing that it's there. So, set your main KPIs for your application and kind of what definitely cannot fail, and at least set alarms at that level, so that those can be API endpoints or whatever. Spend time learning respective AWS tools. I think that's really important, and they are quite powerful and kind of a good place to start. Another way of thinking about them is also that they're like a repository of information that you need to have to understand the state of the system from the outside. And kind of as the last part is that even though there is some information in AWS, I would recommend, at least at scale, and when you have users that you're really depending on or who are depending on your service, to adopt third-party monitoring and operations tools. So the general idea is that you need to have really good ability to navigate data, to navigate between logs, metrics, and tracing data, to automate alert coverage, and to kind of get actionable insights into how to improve your infrastructure. And that's kind of, you either have to build it yourself, or but I would recommend kind of reusing what's already been built. Obviously, maybe a bit biased. The other thing that's going to eat your time and effort is local development environment. So that's also something you should think about quite early on. The fundamental problem is that you can't easily emulate the cloud environment locally, which means you either have to deploy after each iteration in your code. Services can be complicated to run locally, and like the problem that comes a bit down the line is that local and cloud environment will never be completely the same, and they will be different, and they will have differences. Means that if it even works locally, then if you deploy it, sometimes things can still fail. So that's kind of an area also with serverless that you need to think about. So there are a couple of ways around it. As I mentioned, you can kind of emulate cloud services locally. Lambdas are quite easy to run locally. Databases and kind of other services are much more harder. So that's tricky. One of the things we've used a lot is connecting local resources to cloud resources. An example here is if I'm developing a Lambda locally, that Lambda would still connect to a development stage DynamoDB table, or interact with an SQS queue that's in the cloud. Another option is kind of to do cloud locally, which means that you deploy your function code each time to the cloud, and then you test on the cloud. So the deployments are significantly reduced. It's just pushing that small part of the change up into the cloud, and then you can test. And yeah, we also recommend test-driven development. So if your functions are small chunks that you can write unit tests to, you don't need to deploy them at each time when you change some code. You can just kind of use unit test, and that will also cut down the iteration speed, or it will make you more quicker. Yeah, I think the last thing from me is that one of the biggest multipliers also is investing time in learning and experimenting. A large part of that is that serverless is constantly evolving. New services are always being introduced by AWS, and we're also getting smarter around what the future will look like, what are the best practices, and it's changing really quickly. So 2 years, 3 years down the line, we had much more problems. The problems were different. We didn't have mature tooling in the space. Now, like, everything exists already to build really high-class quality serverless applications. I also recommend looking at This Is My Architecture series and serverless customer stories. Those are a great kind of way of seeing how things are built in the real world and kind of getting inspired. Attending summits, meetups, and reInvent has been super useful to us, at least, and it's a great way to connect with developers who are building stuff on serverless and kind of to bounce ideas. And I think a really good resource and kind of what really makes a difference for us as well is the well-architected framework and the serverless lens of the well-architected framework. So there's a lot of things there that kind of enable you to think about the 5 topics below. So operational excellence, security, reliability, efficiency, and cost. So that's a great resource that enables you to think quite deeply about the applications and how to build them before actually building them, and also obviously during and at the time of operating them. Thanks.